The discussion will focus on how to compute for the force due to liquid pressure of on a vertical plate submerged on a liquid. So we are going to consider a flat plate submerged in liquid so that the surface is parallel to the liquid surface. Now, the force F due to liquid pressure above this plate is computed by using the formula force is equal to WHA, where W is the liquid density, H is the distance between the liquid surface and the plate or the typical element, and A is the area of the plate. And since the pressure at the point below the liquid surface is the same in all direction, then the force of pressure on a vertical plate submerged in the liquid can be computed by F is equal to the limit of the summation of W H sub I times delta A sub I, where I goes from I to N. And if we will get the limit as N increases without bound by fundamental theorem of calculus, then F is equal to W is a constant, so we can write it before the integral sign, okay, and W is the liquid density, okay, times the integral of H is the distance of the typical element from the distance rather between the typical element and the liquid surface, and the differential of A is the area of the typical element. And we will extend integration over the entire area of the submerged surface. So the differential of A is the area of the typical element, and H is the distance of the element from the liquid surface. So if we will consider this as the liquid surface, this horizontal line is the liquid surface. We are going and consider this as the vertical element submerged in the liquid. We are going to divide the element into rectangles, okay, typical element which are rectangles. So if we will compute for the force due to liquid pressure on this element, no, we will just multiply the liquid density by the distance of this element from the liquid surface, and we will call that as H sub I, then multiply it by the differential of A, which is equal to the area of the element, the length of the element times the thickness. And if we will get the summation of the forces of the infinitely many rectangles, no, on this vertical plate, then that will give us the force due to liquid pressure on this vertical plate. And to consider some examples, no? Okay, let us have the next slide. And we will consider a rectangular plate 12 feet long and 8 feet wide that is submerged vertically with the longer side on the surface of the water. Find the force on one side of the plate. So we can let this vertical line be the y-axis for convenience, and let this be the x-axis, so that the vertical plate is on the first quadrant in the rectangular plane. And we will let this as the liquid surface. Let this be the liquid surface. Okay, and since according to the problem, the 12 foot edge or side of the rectangular plate is on the surface of the water. Okay, so this is 12 feet, and the width is 8 feet. Okay, therefore, this distance from the x-axis is 8 feet. And if we will divide the rectangular plate into rectangles and consider the representative element, this is the typical representative element, then the thickness of the element is the differential of y, and the length is equal to 12 uh, foot, 12 feet rather. Okay, so if we want to compute for the force due to liquid pressure acting on one face of this rectangular plate, okay, we will use the formula force is equal to the weight density of the liquid, okay, times the integral of h. H is the distance of the typical element from the water surface, and the differential of A is the area of the element. Okay, so we will have W. Okay, since W is a constant, we can write it before the integral sign. And take note that this element is at a distance y from the x-axis. So this is y. Therefore, if we will get the distance of the element from the liquid surface, that is equal to 8, okay? Take note that the width of the rectangular plate is 8. So we will have 8 minus y. So h is equal to 8 minus y. So we have h is 8 minus y. And the differential of A is equal to the area of the typical element, and the area of the typical element is the length of the element times the thickness, which is the differential of y. Okay, hence, the force due to liquid pressure is W times the integral of H is 8 minus Y. Okay, the differential of A is 12 times the differential of Y. And the limits of integration will go from Y is equal to 0 to Y is equal to 8. Okay, so lower limit is 0 and the upper limit is 8. Now please take note that y goes from 0 to 8. And we can write 12, a constant factor in the integrand before the integral sign, which will give us 12w. Then evaluate the integral of 8 minus y dy with respect to y rather. So the integral of 8 dy is 8y, and the integral of y dy is y squared over 2. Okay, now, well, if you want, you can also write this first as 12w times the integral from 0 to 8 of quantity 8 minus y times the differential of y. So that will give us 8y minus y squared over 2, which is the integral of 8 minus y dy. And this must be evaluated from the lower limit 0 to the upper limit 8. And if we will evaluate the integral at the upper limit, so we will have 12w times when y is equal to 8, then that gives us 8 times 8, okay, minus 8 raised to the second power over 2. And if we will evaluate the integral at the lower limit 0, then that will give us 0, so minus 0. Hence, we have 8 times 8 is 64, okay, minus 8 squared over 2 is 32. So that will give us 32 times 12w. And the force due to liquid pressure is 384w. So the force due to liquid pressure is in terms of the weight density of the liquid. Now, of course, if the numerical value of the weight density of the liquid is given, then just substitute the numerical value of W and then compute for the force due to liquid pressure. So again, to solve for the force due to liquid pressure of a vertical plate submerged in a liquid, okay, we have to identify first uh, the distance of the typical element from the liquid surface and then get the differential of A and express the integrand in terms of the variable of integration, which is Y. Okay, so this is the first example. And if we will consider the second example, then let us have a rectangular plate with base 5 feet and the altitude 3 feet. And it is submerged vertically so that the vertex is above the base and 2 feet below the surface of the water. Find the force against one face of the plate. So we have to draw the triangular plate, okay? And for convenience, we let this vertical line be the y-axis and let this be the x-axis. Now, since we have a triangular plate with base 5 feet, okay? So let the vertex of the triangular plate be on the y-axis for convenience. So if this is the base of the triangular plate, then the distance from the origin up to this point, up to this vertex is 5 over 2, since the base of the plate, the triangular plate is 5. So this is 5 over 2. This is also equal to 5 over 2. And the height of the plate is 5 feet. Okay, so from here, from the vertex to the x-axis is 5 feet. Now, according to the problem, oh, sorry, this is 3 feet rather. This is 3 feet, the altitude. Okay, sorry. Okay. The altitude is 3 feet and the base is 5 feet. Okay, so this is 3 feet. And accordingly, also, this vertical plate submerged in the liquid is 2 feet below the surface of the water. So the vertex is 2 feet below the surface of the water. So the distance from the vertex to the surface of the water is 2 feet. Okay, so this is 2 feet, meaning from the x-axis to the liquid surface. Okay, this is the liquid surface or the water surface. The distance of the base to the liquid surface is equal to 5 feet. Okay, 3 plus 2 is 5 feet. Okay, and to determine the force due to liquid pressure acting on one face of the plate, then we use again the formula: force due to liquid pressure is equal to the weight density of the liquid, the water, times the integral within the limits of integration from A to B. So here, y will go from the x-axis from 0 to the surface of the water, which is at y is equal to 5. So y will go from 0 to, 0 to 3 only. Okay, 0 to 3. Okay, since we are just considering the uh, triangular plate. Okay, the height of the plate. So y will go from 0 to 3. Okay, but the distance from the vertex to the liquid surface is equal to 2 feet. And we will consider that in getting the value of h, which is the distance of the representative element from the water surface. And for convenience, no, we can just consider half of the triangular plate. Now, since there is symmetry with respect to y-axis, we can just consider this half. Okay, and the force due to liquid pressure on half of the plate, no, is the same as the force due to liquid pressure on the other side. So we will just multiply it by 2. And if we will let this point be a point whose coordinates are x and y, then the length of the representative element is x. But we have to multiply, of course, the force due to liquid pressure by 2. So uh, the force due to liquid pressure is the integral of h times the differential of a from a to b. And if we will draw the typical element, okay, this is the typical element. Okay, consider this as the typical element. Okay, the distance of the element from the x-axis is y. Okay, so this is y. And the distance of the element from the liquid surface is h. And how do we get h? If this is y, and this is 3 plus 2, that is 5. So h is equal to 5 feet minus y. So h is 5 minus y. And looking at the element, the length of the element is x, and the thickness is the differential of y. Okay, therefore, we will have w times the integral of h. H is equal to 5 minus 1 times, okay, if this is x, then if we will extend this, that is of course equal to 2x, or just multiply the force by 2. Okay, so we will have the thickness equal to dy. Okay, so we have x times the differential of y, and then just multiply it by 2. So the force due to liquid pressure is 2w times the integral of 5 minus y, that is h, times the value of x. Now, take note that the variable of integration is y, and we have x in the integrand. Therefore, we have to express x in terms of y. And we can do that by referring to the right triangle, okay, which is one part of the triangle. Okay, wait. This is the base of the right triangle, and this. We are considering this triangle. Okay, and let this be the typical element, okay? Of course, this is x, the base of this small right triangle, and this is 5 over 2, the base of half of the right triangle. Now, this distance is y, therefore, the height of the small triangle is the height or altitude of the triangular plate, which is equal to 3 feet minus y. So this is 3 minus y. And if we will do ratio and proportion, okay, the base of the small triangle, take note that we have a small triangle here, and it is proportional to the big right triangle. Okay, so by ratio and proportion, the base of the small triangle is to the altitude. So x is to 3 minus y, and this is proportional to the base of the big triangle, right triangle, which is 5 over 2, and the height is equal to 3. So we have variation proportion, and by similar triangles, we have x over 3 minus y is equal to 5 over 2 over 6. Of course, the right member of the equation is 5 over 6. Therefore, if we will solve for x, then x is 5 over 6 times 3 minus y. So x is 5 over 6 times 3 minus y. And we can replace x here by 5 over 6 times the quantity 3 minus y. So that the force due to liquid pressure is 2w times the integral within the limits of integration from y is equal to 0 to y is equal to 3, okay, of 5 minus y times 5 over 6 times 3 minus y dy. So 5 over 6, 3 minus y is the value of x. Now, if we will write 5 over 6 before the integral sign, then that will give us 2 times 5 over 6 or equal to 5 over 3. So that gives us 5 over 3 w times the integral from 0 to 3, and then just get the product of 5 minus y, 3 minus y, which is equal to y squared minus 8y plus 15, and then integrate in y. So evaluating the integral of y squared dy gives us y cubed over 3, okay, minus 8y. Okay, integral of 8y dy is 8y squared over 2 or 4y squared, and the integral of 15 dy is 15y. Then just evaluate it from the lower limit 0 to the upper limit 3. And of course, the integral is the value of the integral at the upper limit 3, okay, minus the value of the integral at the lower limit 0. Of course, the integral at the lower limit 0 is 0. So everything is 0. And we will have 3 raised to the third power over 3 minus 4 times 3 raised to the third power, okay, plus 15 times 3. And if we will multiply the result by 5/3 W, then that gives us the force due to liquid pressure is equal to 30 times the weight density of water. Okay, so as long as we know the working equation that the force due to liquid pressure is equal to the weight density times the distance of the plate, the typical element, from the water surface times the area of the element, then that easily gives us the force due to liquid pressure by integration. No? This is integrated over the whole plate. And we still have another problem here. And this actually involved a trapezoid. Okay, in the first example, we have a rectangular plate. In the second example, we have a triangular plate. Okay, this time we have trapezoid. Okay, so what force must be withstood by a trapezoidal dam 100 feet long at the top and 80 feet long at the bottom and 20 feet deep? Okay, so the dam is 20 feet deep. So of course, we will assume that the water surface is on this upper base. Okay, since we are asked to find the force that the trapezoidal dam can withstood. So we are assuming that the water level is at the top of the trapezoidal dam. Okay, so the length of the trapezoidal dam, okay, is 100 feet long, okay, at the top. So if this is 100 feet long, then this must be 50 and this must be 50 considering the y-axis at the middle. So this is the y-axis and this is the x-axis. Okay, so the y-axis divides the trapezoidal dam into 2 equal parts. Okay, so if we will draw a typical element, okay, this is the typical element, but we cannot do ratio and proportion on this portion of the dam. Okay, so what we can do is to divide this into 2 parts. Okay, we will divide this into 2 parts. Now, please take note that this is 40. This must be 40 also. Hence, this part is 10. And we will let this portion be x. Okay, therefore, the length of this element on the first quadrant is equal to 40 plus x. Okay, this is 40 plus x. Okay, and since we have the other half, okay, on the left, on the second quadrant, then we will just multiply the element by 2. So that will give us 40, 40 plus x times 2, then times the thickness dy. Okay, that is the differential area. Now, what about h? Now, the distance of this element from the x-axis is y. And since the height of the dam or the depth of the dam is 20 feet, okay, then the distance of this element from the water surface is equal to h, and that is 20 minus y. So h is equal to 20 minus y. Hence, the force due to liquid pressure is W, okay, times h, which is 20 minus y, times the length of the element, 40 plus x times 2 times the thickness dy. And limits of integration will go from the bottom of the trapezoidal dam up to the top, which is equal to 20. So limits will go from 0 to 20. Okay. Now, the problem here is we have x here in the integrand, and the variable of integration is y. Therefore, we have to express x in terms of y. And as mentioned earlier, we cannot simply do ratio and proportion on this portion. Okay, we need to divide this and consider this right triangle. Okay, take note that this is equal to 10, okay? The base of this small triangle is x, and this is y, okay? And this is 20 minus y. So, considering that portion of the rectangle here, then this is 10, this is x, okay? This is y, and the height is 20. Therefore, by ratio and proportion, the base to the height, x is to y, is equal to 10 is to 20. Okay, so we will have x over y is equal to 10 over 20. And 10 over 20, of course, is 1/2. Therefore, if we will solve for x, then x is y over 2. And we can replace x here by y over 2. And if we will multiply 20 minus y by 40 plus y over 2, that will give us 1,600 minus 60y plus y squared times the differential of y. And evaluating this in the integral in y will give us 1,600y minus 60y squared over 2, which will give us 30y squared. Then integral of y squared dy is y cubed over 3, limits going from 0 to 20. And if we will replace y by the upper limit 20, okay, minus the value of the integral at the lower limit 0, that gives us the force due to liquid pressure is equal to 52,000 over 3 times the weight density of water, which is W. So force due to liquid pressure is 52,000 over 3 W. Okay, so this is how to get the force or to compute for the force due to liquid pressure of a vertical plate submerged in a liquid. So the force is equal to the weight density times H times the differential of A, okay, or the differential of A. And we have to evaluate this from the lower limit A to the upper limit B. But of course, our focus, of course, is on the rectangular element if we want to get H and the differential of the area. Okay, so easily we were able to get the force due to liquid pressure. So just be careful when doing ratio and proportion, especially if we have a trapezoid. You do not include the constant part here. Take note that this is uh, in the form of a rectangle. So you do not include this rectangle, this part of the trapezoid in ratio and proportion. We can only do ratio and proportion here on the triangular edge.